Hello students, in the last project we studied the compressor components, and in this class we will start studying the turbine components. Before learning about turbine components, let's take a look at what the first picture shows. I think many students already have the answer. It is a water turbine, so how does the water turbine rotate? It is through the flow of water that it can impact the blades of the water turbine, causing the water turbine to rotate. The second picture is a wind power generation device. When the wind blows through the blades of the wind power generation device, the blades will rotate, thereby driving the generator to rotate and generate electricity. The third picture is the turbocharger used in the car engine. When the exhaust gas of the car flows through the radial turbine, the exhaust gas will impact the turbine blades to rotate. The rotation of the turbine will drive the coaxial compressor to rotate, inhaling more fresh air for the engine cylinder body, thereby generating stronger power. The fourth picture is the hydropower equipment used in the Three Gorges Dam hydropower station. When water has a certain gravitational potential energy and flows through the impeller of the generator, the impeller will rotate to generate electricity. From the above four pictures, students can see what common characteristics they have. Their common feature is that they are all components that generate mechanical energy and convert other forms of energy into rotational mechanical energy. In an aircraft engine, the component that converts mechanical energy is the turbine. The function of the turbine is to convert part of the kinetic energy and thermal energy of high temperature and high pressure gas into rotational mechanical energy, thereby driving the compressor and other accessories. When the turbine is working, it has the characteristics of high power, high temperature, high speed, and high load. The performance indicators of a turbine include turbine pressure ratio, turbine work, turbine efficiency, turbine power, etc. The turbine pressure drop ratio is the ratio of the total pressure at the turbine inlet to the total pressure at the turbine outlet. It is expressed as P3 star divided by P4 star. The larger the turbine pressure drop ratio, the more mechanical energy the turbine converts. Turbine work is divided into ideal work and adiabatic work of the turbine. The ideal work of the turbine refers to the work output by 1 kilogram of gas through an ideal process expanding from the inlet to the outlet, which is called ideal turbine work. The adiabatic work of the turbine refers to the work output by 1 kilogram of gas through an adiabatic process expanding from the inlet to the outlet, which is called ideal turbine work. Turbine efficiency is the ratio of adiabatic turbine work to ideal turbine work, expressed as WT divided by WST. Turbine efficiency is the work output by the turbine shaft per unit time. Next, let's learn about the classification of gas turbines. Gas turbines can be divided into axial flow turbines and radial turbines according to the flow direction of the airflow. As shown in the figure, the left picture is an axial flow turbine and the right picture is a radial turbine. The gas flow direction of radial turbine is perpendicular to the turbine axis. Radial turbine has the advantages of large single-stage power, good working, reliability, simple structure, convenient processing, and high efficiency for small flow turbines. However, radial turbine is large in size and generally cannot be composed of many stages, so it is generally used in small and micro gas turbines, ground gas turbines, turbochargers, etc. The gas flow direction of the axial flow turbine is consistent with the direction of the turbine axis. The axial flow turbine has the advantages of small size, large gas flow, large shaft power, high speed, and good cooling. Therefore, it is widely used in large and medium-sized aviation turbine engines. In this project, we also focus on the study of axial flow turbines. The axial flow turbine is composed of a rotor and a stator. The turbine rotor includes working blades, turbine discs, turbine shafts, and connecting parts. The turbine stator includes the turbine guide vane and turbine casing. Next, let these look at the two characteristics of the axial flow turbine. The first characteristic is that the stator of the axial flow turbine is in front and the rotor is in the back. Students can think about why it is designed like this. The reason is that the airflow must be guided to the direction where it can directly impact the turbine blades in order to impact the turbine blades. Just like the small windmill we played with when we were young, if you blow at the windmill blades, the windmill will easily rotate, but if you blow it sideways or at an angle, the windmill will not rotate so easily. The second feature is that the meridian channel of the axial flow turbine is expanded. Since the airflow needs to expand and accelerate inside the turbine, it has greater kinetic energy to impact the turbine blades. In order to expand the airflow, the expansion volume of the airflow will become larger, so the meridian channel of the turbine must be made expanded. Students, in this class, we learned about the role of turbines, performance indicators, and classification of turbines. Students must review what they have learned after class and complete the self-test questions in time. Thank you, everyone.